Welcome. In this lecture, we will see some of the diagnostics for multiple linear regression, and one more concept we will introduce, which is known as lack of fit and test for lack of fit. Essentially, the diagnostics measures lack of fit and its tests will be discussed, and for model diagnostics we will be using standardized residuals, then studentized residual, then pre-statistics, and also we introduce leverage points, or influential observations, and these are the things will be discussed for diagnostic. And then as I told you, we will go for lack of fit, LOF, related to regression, everything related to regression, linear regression, multiple linear regression. So, let us see the two standardized residuals. By this time you understand what is the meaning of standardized. So, you have I equal to 1 to n number of observations. So, you have n number of residuals, E1, E2, EI, En. So, what is the expected value of EI? It will be 0. So, by standardized residual we mean we will create suppose di, where di equal to EI by MSE. You know the concept of MSB also. So, this is nothing but EI by sigma square cap. The sigma square cap is estimated by MSE. So, it will follow normal distribution. And it variance for all standardized. So, what you have done? You have essentially, this is nothing, we can write EI minus expected value of EI divided by variance of EI square root, that is the standardization. So, this one is 0 and like this. So, it should be almost normal 0 1 unit normal. And what happened is, suppose this is uninormal distribution, this is minus 3 and this one is plus 3. It is seen that most 99.7% observation will fall under this. So, then most of the observation fall minus 3 to plus 3. So, if any of the standardized residual is more than 3 in absolute value, then what we can say that it is not normal, it is outliers kind of things, or other way I can say that it is not normal. So, this is what is the standardized residual will tell you. Standardized will tell you about two things. Obviously, we can assume that as it is for that much plus minus 3 sigma level away. So, we can say also say that they are outliers also, sometimes we can say in this manner also. And or other way you can say that this is not normal. Now, second one is your studentized residuals. So, before studentized residuals, you just know what is hat matrix. So, all of you know that y cap equal to x beta cap, and if I put the beta cap is nothing but x transpose x inverse x transpose y, then the resultant quantity is x transpose x inverse x transpose y. Now, you say that H equal to x transpose x inverse x transpose, and this is H y. This H is a very interesting matrix which is known as hat matrix, and what it says, it maps the vector of observed values into the vector of fitted values. So, that means the hat matrix gives you information about every observation, some statistic about every observation. That is the means, that is a beautiful thing, that beta coefficient talks about the influence of the variable on the response, whereas from the hat matrix you will know that influence of every individual observations, so on the response. That is the interesting one. So, if y cap is h y, then residual will be y minus y cap, which is y into I minus h. Okay. Now, what we require, suppose if we require that covariance of E, then this will be I minus h covariance of y, which is nothing but variance. So, sigma square I minus h. Okay. Now, then what is the variance of ith observation? That variance of ith observation will be sigma square 1 minus the ith diagonal elements of the H matrix, which is H I I. Means we can write like this, that H 11, H 22, H I like H n n. We have n observations. So, n cross n this will be, and definitely this will be H 1 2 like this, other values will be there, The diagonal elements H I I, this is very important elements, this is the influence of the observations on the regression line or regression plane. So, then your variance for ith variance will be this. So, ith residual variance will be sigma square 1 minus by this. Then the studentized residual is if we say this is R I, which is E I minus variance of E I, which is sigma square 1 minus H I I. Obviously, you can write this one, this divided by M S E 1 minus H I I. And all those things you know. And then what will be the variance of R I? Variance of R I will be 1, because it is this minus the mean value will be 0 by this, the variability, this also 1, mean 0, mean of this 0, variance is 1. So, this is known as studentized residual R I. It is similar to standardized residual, but if some of the observations in standardized residual, what happened, you have considered E I by sigma, that is M S E, square root of M S E you consider, but here you are multiplied this term. If everyone is contributing equally, fantastic, but otherwise what happen if there is some of the observation contribute more, HI value will be more, and then its contribution to the residual will be also more. So, okay. So, this is what is studentized, otherwise in interpretation point of view they are similar to standardized residuals. Now, we will come to another very important one is PRES statistics or PRES residual. PRES stands for prediction error sum of squares. What is the procedure here? Procedure is you have I 1, 2 dot I n number of observations and you fitted a model y equal to x beta plus epsilon. Instead of this, you do one thing, you fit a model y I equal to x beta, or if I say x beta I something like this plus epsilon or epsilon I something like this. What I mean to say, you remove the ith observation while fitting this model. Then what happen? If you remove the ith observation, you and then using the fitted model, you predict the value of ith observations. What you are doing? You are fitting the same regression model, not considering all the data points, ith observation you are removing or omitting, then using this fitted model y equal to y fitted equal to x beta cap, you are predicting the ith observations. Then the error what you are getting, that E I, E within bracket I, this one will be nothing but that y I minus y I cap, because this within bracket I we are using, we are saying that when you have fitted this model, you have not considered the ith observations. Now, you can repeat the same thing. Suppose you start with first observation, find out this, what is this E 1, second observation, find out this like this E I, like this E n. So, you have total n number of residual values. These are all basically predicted residuals basically, and these values you are getting using this kind of approach. And then you find out the PRES. What is the PRES will be? PRES will be sum total of all those residual square I equal to 1 to n. This is nothing but sum total of I equal to 1 to n, y I minus y I y within this cap square. Okay, so this is what is known as PRES. So, by listening this much, you may be thinking that you have to go for n number of regression, means n times you have to done the regression, first omit the observation 1, then omit observation 2, and like this way you continue up to n. If n equal to 1000, that means you have to run the program 1000 times. Okay, but it is not so, because even in from the one regression model also, one time fitting regression you will get, and that is interestingly that PRES is sum total I equal to 1 to n E I by 1 minus H I, sorry. So, you do not require to go for n times doing the regression, omitting one observation at a time. You feed the regression using all the values and then find out HII and also find out EI. Then PRES is I equal to 1 to n EII by 1 minus HII, that is what is the our E within bracket I. So, that means if you see the studentized residual type, that time 1 minus HI we have subtracted, but anyhow PRES consider this space is this. Okay. Then then we will go for suppose that here what happened, every observation which is omitted is predicted using the regression model fitted through rest of the observations. Then we can get also R square prediction. This will be 1 minus press by SST. Usually what is R square? R square is 1 minus SSE by SST. Here instead of SSE we are using press. Okay. Now let us see the example results. So the viscosity example what we have I have discussed earlier. So here the when we have computed R square using R square equal to 1 minus R by SST, we got that value is 0.93. Now when we are using R square prediction using the spread statistics, this R square prediction value is coming 0.89. So what is the conclusion here? We could expect the model can explain about 89% of the variability in predicting new observations as compared to approximately 93% of the variability in the original data explained by the least square fit. The overall predictive capability of the model based on this criteria seems very satisfactory. Okay. Now come to the influential diagnostics or influential observation. Here one is leverage point. What is the leverage point? The elements H I, this should be H I J. Okay. The elements H I J of H may be interpreted as amount of leverage exerted by Y j on Y I. Okay. Inspection of the element H can reveal points that are potentially influential by virtue of their location in the X space. So, as I told you, the leverage points, when if you see the diagonal elements of H11 to Hn, so these are the basically the influence exerted by each of the observations. So, and also off diagonal elements are also there. So, there what happened, the actually the if when we compare the yi actual observation with the predicted observations. So, that sense you have to think of. Okay. So, another major one major used for this influence generation or quantification of influence, that is known as d beta measures, distance measure d1 or immediately or di. So, it is basically di. So, this is nothing but what happened the same way that you eliminate the ith observations and feed the regression line, and then the beta whatever the estimated value you are getting, and when this estimated value and the full model means full means the including all the observation you got beta value, then using these two and the X design matrix, this kind of distance is measured. Here it is di. This distance is measured. If any of the di values is greater than 1, then that is influential. Okay. So, here also you may be thinking that you require to go for n number of regression. It is not, because we have this a hat matrix. From this hat matrix, this di can be computed like this. Ri is studentized residual, that is also you know. P is the number of parameters to be estimated known, and HII is coming from hat matrix. So, if any d value is more than 1, that is influential. Now, I will come to another interesting concept, which is known as lack of fit and how to test lack of fit. First, let us see this diagram. Let us assume that this is x, the regressor, and y is the dependent variable. Here I am showing with one regressor variable, but it can be for many regressor variable. Suppose x 1 is the first observation, x 2 second observation, first fixed value for x. These are the m number of fixed values for the regressor. Now, let the this one ith one is the x I 1, and here suppose you have conducted experiment keeping x at x I, suppose n number of times or n I number of times. So, your observations will be y observation will be n I here, n I number of observations you will get, and similarly here also n 2, here n 1, and like this. And you have seen in one way analysis of variance also, suppose keeping the power factor 165 number of observations experiment were done like this. So, in the same manner. Now, when you fit the regression equation for one factor experiment case, you will get a regression line like this. So, any point suppose for so that means what is this point on the regression line? This point on regression line is y I cap. So, y I cap is the value of y when x equal to x I. So, this is basically I can say the expected value of y I given x equal to x I kind of things. Okay. So, this is y I cap. Now, you have n I number of observations here. So, this n I number of observations, if you compute the mean value, that is y I bar may be falling here. Now, you then what is the error here, total error here? If I consider a general, suppose you think of a particular observation y I j, I from 1 to m, the m regressor fixed values, and j is basically the replication at a particular fixed value of x. So, now what happened? The total error for a particular observation y I j will be that y I j minus y I cap. So, this can be, so y I j minus y I f can be partitioned like this, y I j minus y I bar. That means, the mean value or average value of all the y when x equal to x I, which is coming here, plus we can write that y I bar minus y I cap. So, then each of the observation here is subtracted by their observations means. So, this is giving you pure error, and then remaining one, because total error is what? Every observation minus the predicted value. So, the pure error, if pure error is this basically every observation minus those observations mean value or average value, then the rest is lack of fit. Rest is lack of fit. So, actually what we mean to say, there is lack of fit if the mean of the observed y for x equal to x I will not coincide with the predicted value. If it is not does not coincide with the predicted value, so that is your lack of fit. Okay. So, now this is basically the deviation part. You take square it, you square this side, take the sum for across all j equal to 1 to n I, and across all I equal to 1 to m, and you do algebraic manipulation, you will be getting this equation, where you will be getting the sum square error, which is sum square pure error plus sum square lack of fit. Okay. Now, see this slide. So, I told you this is this. So, sum square prior error is yij minus y bar square, this one, and you have ni observation for at the xi level. So, as there are m such levels, so total number of that degrees of freedom available with the pure this error is n minus m, and lack of fit you are getting from this formula that ni is this. Okay. So, that means what happened now lack of fit is computed. So, let us compute a statistics to say that whether lack of fit is significant or not. So, this statistics is F0 SS lack of fit. What is SS lack of fit? This one. By its degree of freedom, by its degree of freedom means what happened? How many x levels are there? So, I equal to 1 to m, every level you are computing, and you have also 1 degree lost. That is why what is happening for p number of parameters, you have lost that p value degrees of freedom. So, m minus p by SS pure error by its degrees of freedom, because pure error degrees of freedom, the remaining degrees of freedom from SSE. So, that is n minus m. So, you are getting ms lack of fit by ms pure error. Now, expected value of ms pure error is sigma square, and the expected value of ms lack of fit is sigma square plus this quantity. So, what is beta 0 minus this or beta 0 plus this? This is nothing but your the predicted value. So, an expected value of yi, that also that is the value which is basically falling on the regression line. If they coincide, this value will become 0. So, that means lack of fit and this will be same. So, but if they do not coincide, this quantity becomes more than 0. So, expected value of ms lack of fit will be more than sigma square. If the true regression function is linear, then what happened? Expected value of yi will become this beta 0 plus this. In that case, this becomes beta 0 plus this, means this quantity becomes 0, and as a result I told you expected value lack of fit become sigma square. If the true regression function is not linear, this will not become 0, this quantity not become 0, because expected value of yi is not this. In that case, this quantity become positive and there is more than the lack of expected lack of fit is more than sigma square. If the true regression line is linear, now the first case, then this quantity f 0 follows f m minus b m minus 1 distribution, and what happened, the regression function is not linear, then your f 0 the computed value will be greater than the theoretical f value. Okay. So, thank you very much for your patient hearing, and I hope that you got enough inputs for regression and also enough inputs for ANOVA, apart from the basic statistics part what we have given you earlier. So, I can tell you that the statistics part for understanding the design, understanding and analyzing the design experimental data. So, that is covered now. One important thing is to be covered further from the theoretical point of view is the sample size. How to calculate the adequate sample size under different situations. So, that will also be discussed. In fact, when we go for other lectures where we will bring all those concepts again, all those sample size part we have discussed, but again we will bring all those things together. Okay. Thank you very much.